Hello everybody. So today we will start talking about planar graphs, and I'll start with a definition. So a graph is called planar if it is possible to draw it on the plane, so on the paper, say, so that the edges only intersect at the endpoints. So there are no internal intersections of edges. Another definition is that a drawing of a graph with no internal intersections, so the good drawing basically, is called a planar representation. So let's consider some examples. So here is my first example. Here we see a graph, and the way it's drawn, it's clear that we see that the edges do not intersect each other than at the endpoints, at the vertices. So therefore, this is a planar representation. A representation of a planar graph. Now, in the second example over here, we see that this graph, it has a lot of internal, also the edges do have internal intersections. So this is not a planar representation. So it's not a planar representation. But it's not hard to see that one can remedy this. One can draw the same graph in a different way, so that there are no intersections anymore. So how are we gonna do this? Well, basically, I'll just take out this edge and replace it with the edge going around like that, and also I will redraw this edge, also making it go around like that. So if I do so, then this becomes a planar representation, and therefore this graph is planar. So it is not so this particular drawing is not a planar representation, but the graph is planar. Once again, the reason is that we can redraw it in a different way so that there are no internal intersections of edges. So my another example, third example here is the graph K33. So this is a complete bipartite graph with two partites of size 3. So clearly, with the way we draw it, the way I've drawn it here, it has a lot of intersections, and we can try to remedy this. Say, okay, let's take out this edge and draw it going around like that. Let's maybe take out also this edge and also draw it going around like this. Then we can do something similar with let's say this edge. No, this edge. Well, say with this edge, right? So this edge we can still go around like that, but it's kind of but now we are stuck. We need to redraw one of these two edges, and there is no obvious way to do that. We cannot really draw or make them go around. They will have to intersect some of our edges anyways. So in fact, we will prove a little bit later that K33 is not planar. So it is not possible to draw it on the plane without self-intersections. However, what I did right now, it's not really a proof. I just tried to draw it and I failed, but it doesn't mean that. I mean, it does not. I didn't really check all the possibilities. Maybe there is some clever way to draw it without intersections. I don't know. So I want to highlight that proving that a graph is not planar is rather tricky. It's not really possible to check all the possible drawings because there are just infinitely many of those, so we need some other instruments, some other approaches to how to do that. And so let's start kind of developing these instruments, developing ways of proving that some certain graphs are not planar. In particular, K33 is not planar. So to do so, I will need more definitions. So our next definition is that of a region. So if we have a planar representation of a graph, then a region is a maximal portion of the plane such that any two points can be connected by a curve that does not intersect the graph. So basically connected components of the complement. So let's consider an example. So here what I wanted to do, I wanted to draw a complete, so I wanted to draw complete graph on 4 vertices, so K4. So let's draw it. So we have a foregone, and then we need to draw its diagonals. So if I draw both diagonals, they will intersect. But I can go around. I can make the second diagonal go around like that, and that's a planar representation. So now here we get, let me maybe move it a little bit. See here. Okay. Here we get regions. Let's see. So here is a region. This triangle is a region. So any two points in this yellow area can be connected by a path, by a curve, without intersecting the graph. Then the other triangle is also a region. Then we have this curved triangle. Say, so this one. That's another region. And finally, we have this outside region called exterior region sometimes. So this is my exterior region here. So again, we can connect any 2 points in this gray area. We just need to go around our graph. So I conclude, so yes, so maybe I should say that this gray thing is called exterior region. Sorry, exterior region. And in total, we got how many regions? We got 1, 2, 3, 4 regions. And I also want to record so how many. So we have 4 vertices, and we have how many edges? 1, 2, 3, 4, 5, 6 edges. 4 vertices and 6 edges. Now, my next example is about trees, and I've drawn a tree here, but just for illustration. But the point is that if I have a tree, then we just have one region here. So let me draw it. So because with the tree does not have any cycles, and that means that we can go around it and reach any point in the complement without crossing the tree. So we can conclude here that the number of regions is 1, and well, we might have any number of vertices, but the number of edges, as we discussed before, as we proved previously, is just one less than the number of vertices. So we have 1, n, and n minus 1. My next example is cycles. So if I have a cycle, then we have clearly two regions, one exterior, one interior, and therefore, so R is equal to 2, number of vertices is, well, let's say n, and number of edges is also n. So the cycle has as many edges as it has vertices. Okay, my next example is just this graph I copied from above. So let's see, we have one region here, another region here, then third region here, and we have the exterior region, which I know traditionally draw in gray, like that. So we can write that number of regions here is 4. I can count the vertices, 1, 2, 3, 4, 5, 6, 7, and number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, one more example here. So this is this graph we considered in the second example over here, but instead of having it with this self-intersection, I've drawn it so that we have a planar representation. So my two of the diagonals go around here to avoid self-intersections. So let's consider the regions. So we have this region, then we have say this region, this triangle, we have this region, we have say this region, and then we have, I don't know which color do I want to use. Let's say this. We have this region as well, and finally we have the exterior region. So let's count. Number of regions is equal to 1, 2, 3, 4, 5, 6. Number of vertices is 5, and number of edges, Q, is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges. Finally, I wanted to illustrate here that sometimes the same graph, exactly the same, so is up to isomorphism, I mean, so two, maybe more precisely, two isomorphic graphs might have very different planar representations. So here I draw, so basically I have a 5-gon with two diagonals coming out from the same vertex. But the point is that I can draw them in a very different way. So I can draw it as a triangulation of this 5-gon, so drawing both diagonals inside, or I can draw one of the diagonals inside and make one of them go around. So in particular here on the right, I have a region which is a 4-gon. Or maybe I should use different. So then we have a 4-gon, or quadrilateral, I guess. And there are no quadrilaterals on the left. So clearly these two drawings are very, very different. However, if you count the regions, you get the same number. So let's color. everything as usual. Say like this, and we have gray around. And on the right, we also have 1, 2, 3, and 4 regions. So we can write that we have, in both cases, we have 4 regions. We have 5 vertices, and what am I doing? This was not Q, this was R. And edges, we have 5, 6, 7 edges. All right, so we have these examples, and I'm not sure if you noticed this pattern in this. I actually think that it's not that easy to notice this pattern unless you kind of know to expect it. But there is a certain relation that is always satisfied for these 3 numbers. And well, so I'm showing it to you in case you will notice it. But well, let me just formulate this. So this relation is called Euler's formula, and that's our theorem for today. So if we have a graph, it is important that the graph should be connected. And I say planar graph, but actually I do need some planar representation in order to count regions. So let's say that we have n vertices, q edges, and r regions. Then we always get n minus q plus r equal to 2. So let me emphasize one more time that it is important that the graph is connected, otherwise it's not gonna work. So let's prove this. So yes, so if you look at the examples, you indeed will notice this. So the way I was writing, so you need to add up r and n and subtract q. So I have 4 plus 5 minus 7, that's 2. 6 plus 5 minus 9, again 2. 4 plus 7 minus 9, 2. Then for cycles, I have 2 plus n minus n. So n cancels out, we get 2. Same for trees, 1 plus n, maybe I should write it, 1 plus n minus 1 is 2. And for K4, I also have 4 plus 4 minus 6, again 2. So every time I get 2, indeed. And that's our theorem. So let's prove it. We are going to prove it using induction in the number of regions R. So your textbook actually uses induction in number of edges. So it's a slightly different proof. So, but I think it's nice to have different proofs. That's kind of that's always nice to have alternative approaches. So the base case is R equal to 1. So what if we just have one region, that means that our graph has no cycles. Well, indeed, if we have a cycle, if our graph has a cycle, then well, let's take any edge on this cycle, maybe this edge here, and then let's take 2 points just across this edge, near this edge, like that. Then it's clear that we cannot really connect these 2 points by a curve without intersecting our cycle. So, so to connect them, we would have to intersect our cycle. So if we just have one region, that means that the graph has no cycles, and therefore it is a tree. So by definition, I mean, we did assume that the graph is connected. So it's connected and has no cycles, so it is a tree. But for a tree, we already know that everything works out, because number of edges is equal to n minus 1, where n is the number of vertices, and we have one region, so we got n minus 1 plus 1. So n cancels out and we get 2. So the base case checks out. Now for the inductive step, let's say that we have, let's say that we already proved for number of regions less than R, and now we want to prove it for a number of regions equal to R, and R is greater than 1. But if R is greater than 1, that means that implies that there exists an edge E such that separates two regions. So we have a picture like that. So we have this edge in purple here, and and we have two different regions on either on the sides of this edge. So it kind of separates these two regions. Well, indeed, if we have more than one regions, we just need to take one point in one region, another point in another region, and just connect them by any path, really, maybe by straight interval. So since those points were in different regions, this interval will intersect some edges. And at least at one of the intersections, we will switch from one of the regions to another. Otherwise, we would stay in the same region. So, anyways, that means that there exists an edge that separates two regions. If we have more than one region, we always have such an edge. Now, what that implies is that this edge E has to belong to a cycle. It cannot be a bridge. Well, indeed, if it is a bridge, then after erasing it, the graph becomes disconnected. And what that means is that if I have 2 points, one on one side of the edge and the other on the other side of the edge, then we can connect them by going. So yes, once again, if it does not belong to any cycle, so it has to be a bridge then, and after erasing it, the graph becomes disconnected. And what that means is that this upper part of the graph has to be a connected component. And what we can do, we can just go around this connected component like that. I can kind of follow it closely like this, and I will eventually go around the whole thing, and then I can reconnect to this point. So once again, if E is a bridge, then it cannot really separate two regions. So bridges don't separate regions. Therefore, E is not a bridge, and then that means that if we erase this edge E, consider the graph G without E, then well, it is still connected, and we still have a planar representation. We just erase this edge, and we get a planar representation of G without E. And this planar representation will have one edge less and one region less than G, right? So because after we erase E, now R1 and R2 become just one region, so they are not separated anymore. So since we have less regions now, we can use the inductive assumption. So by inductive assumption, Euler formula holds for G without E. So that means that n, number of vertices is still n, number of edges is so maybe I should write it here. Number of vertices in G without E is still n. Number of edges in G without E is one less than in G, so it's Q minus 1. And number of regions, okay, let me write it that way. So number of regions of G without E is R minus 1. So number of regions also become one less. So by inductive assumption, we have that n minus Q minus 1 and plus R minus 1 is 2. But those ones, they cancel out, and we get n minus Q plus R equal to 2, which is the formula we needed to prove. So that's it. That's the end of the proof. So essentially what is happening here is that we say that if our graph is a tree, then everything is fine. We know that there is just one region and number of edges is one less than number of vertices, so we get the formula holds. And if it's not a tree, then we can take any edge that separates two different regions, and actually any edge that is not a bridge will separate two regions. And so we take any edge which is not a bridge, and if we erase it, number of regions decreases by 1, and number of edges decreases by 1, and we can continue doing so until we get a tree. And so therefore, since on every step number of regions and number of edges decreased by 1 and number of vertices didn't change, that means that the Euler formula, well, it holds for the tree we got in the end, but then it has to hold in the beginning for the whole graph as well. So that's it. That's our theorem, and that's our lecture for today. So in the next lecture, next video, we will use Euler's theorem to prove that certain graphs are not planar.